So good afternoon, everyone. My name is Francesco Petruccione, and I'm the interim director of NITheCS, which is our National Institute for Theoretical and Computational Sciences. Yeah? And this is our first mini-school in 2023, which is actually not fully correct because in February we hosted the famous summer school, which is roughly the equivalent of 5 mini-schools. So, but this is the first formal mini-school, and we hope that also this year we'll be able to offer you a nice range of monthly mini-school to cover interesting topics. Yeah? And the MARC mini-school is an introduction to solitons and solitary waves in physics and mathematics. That is a topic which is really very interesting to me because in younger ages, I also worked on some soliton problems. Yeah, so that's really going back in time. That's really very nice. And we start the mini school with a talk by Professor Boris Malomet on multidimensional solitons. Professor Malomet received his PhD in 1981 from Moscow Physico-Technical Institute, and he did his habilitation at the Institute for Theoretical Physics of the Academy of Sciences of Ukraine in 1989. Yeah? Since 91, he's based at University in Tel Aviv, which is, I guess, his current affiliation. Yeah, and he's a professor in holding the chair of optical solitons. Yeah, so which sounds appropriate. Professor Malomet was for many years one of the editors of Physical Review Letters, and he's now the editor of Physics Letters A and Chaos, Solitons, and Fractals, and he sits on the editorial board of other journals. Yeah? He's a senior member of the Optical Society of America, and of course he's working in the field of nonlinear optics, solitons, with various applications that he will speak about, I guess, today. So, Professor Malomet, thank you very much for being with us this afternoon and for agreeing to share to the South African community some of your wisdom. I see you're already sharing your first slide. You're most than welcome to start your presentation. And before you start, I always forget to remind the participant to please make use of the Q&A facility to ask questions, and at the end of the talk, you're welcome to raise your hand, and we will give you the opportunity to ask a question in person. Yeah, and Dr. Daniel Sadamant, Professor Herbert Weigel, and Ilya Sinaisky will help at the end of the talk moderating the question. So, Professor Malomet, now it's your show. Thank you very much.
Okay, thank you very much, Professor Petruccione, and I would like to thank the organizers for the invitation to give this talk. So the title of the talk was already mentioned, and you can see it on the screen. Okay, so to talk about multidimensional solitons, it is relevant, first of all, to remind some well-known, actually classical results concerning ordinary solitons. Ordinary solitons usually are nonlinear localized excitations, which usually exist in essentially in one-dimensional systems, in one-dimensional geometry. Solitons, or the full name of these objects, are solitary waves. These are localized self-trapped excitations in diverse physical systems, and they are able to maintain their localized shape due to the balance between nonlinear effects, such as typically self-attraction of the physical fields, and linear effects, which try to actually stretch this wave and to make it broad. So these are classical effects such as dispersion and diffraction. And in many cases, especially in one dimension, it's possible to find a stable balance, stable equilibrium between the nonlinear trend to self-compression of the wave field, and on the other hand, the linear trend to expansion of the field, and the result of this stable equilibrium, solitons are created. So the work with solitons was actually very intensive in several fields of physics, such as nonlinear optics and studies of the so-called matter waves in Bose-Einstein condensates and ultra-cold gases, and plasma physics, and in hydrodynamics, and in many other areas. So probably the most important one-dimensional equation which gives rise to stable solitons is this celebrated equation, which is written here. It's written in the scaled form so that it does not include any free parameter, and it is written for the complex wave function psi. So this is a celebrated nonlinear Schrödinger equation. Elementary fact is that one can immediately find, just by a straightforward substitution, a family of exact solutions, which are written here in the analytical form. So this is the elementary function hyperbolic cosine. So this family of these solutions are localized, and they depend on two free parameters. So one parameter is called, both parameters are real. So generally speaking, the solution is of course a complex solution because I is imaginary unity. So the nonlinear Schrödinger equation is written as well as the linear Schrödinger equation for the complex wave function. And therefore, the solution is also complex, and it depends on two free real parameters. One is eta, and eta has actually it accounts for two properties. First, eta determines the amplitude, the maximum value of this solution. Simultaneously, as it is seen from this expression, 1 divided by eta essentially determines the localization size. In other words, the width of this soliton. And the other independent free parameter is c. C has a very simple meaning, as we see from here. It is actually the speed at which the soliton can be traveling. So if c is equal to 0, this is a quiescent soliton with 0 velocity, and we may have a solution in which the soliton can be moving at any positive or negative value of velocity c. And simultaneously, if you can look at the expression for the phase of the soliton, you see that c, when the soliton is moving, it also develops a term in its phase, which is a linear function of the coordinate, and the coefficient in this term for the phase is also determined by c. Okay, so very well known and extremely important fact, which was discovered back in 1971 by two Russian physicists, Vladimir Zakharov and Alexei Shabat, is that this equation, actually two nonlinear Schrödinger equations, there may be the equations that we started to discuss, and there is also the nonlinear Schrödinger equation with the opposite sign in front of the nonlinear term. It has completely different solutions. It does not have usual solitons. It has a solution in the form of the so-called dark solitons, but fundamental important fact discovered by Zakharov and Shabat more than 50 years ago is that both these equations are exactly integrable ones. So there is a sophisticated transformation, the so-called inverse scattering transform, which makes it possible to replace this equation by a system of two linear equations. So in that sense, this nonlinear equation can be made tantamount to some rather complex but nevertheless linear system. And this fact is extremely important because that linear system admits a huge number of non-trivial exact solutions, and eventually then they can be transformed in a very large number of non-trivial solutions for the nonlinear Schrödinger equation. So the simplest solution gives those elementary solitons, which can be found even we don't know anything about integrability, just by an elementary substitution. But then the integrability demonstrates that there are extremely non-trivial solutions. For example, if we take a superposition of any number of those fundamental solitons, these superpositions can also be described by exact analytical solutions. They're not very simple, but nevertheless, they're available in the exact form. So a superposition of any number of solitons is available in the analytical form. Also, this nonlinear Schrodinger equation being integrable, it admits very interesting solutions in the form of bound states of two or several solitons. So roughly speaking, one can prepare an input in which two or several solitons are put on top of each other, and they can form an exact analytical solution in the form of the higher order soliton, which is frequently called the breather. It's called the breather because unlike this stationary elementary soliton, the breather superposition is always a solution with some internal dynamics, periodic oscillations of its shape. So to say, it is a breathing solution. For this reason, it's usually called the breather. And experimentally, solitons, which are predicted by the nonlinear Schrodinger equation, they were discovered in many different physical settings. In particular, very important results were obtained in nonlinear optics. So soon after the integrability of the nonlinear Schrodinger equation was discovered by Zakharov and Shabbat, just 2 years later, Hasegawa and Tappert used this exact solution, and they actually were able to demonstrate that the propagation of light in nonlinear optical fibers can be approximately described by exactly the same equation. And therefore, they predicted that light which propagates in nonlinear optical fibers because of the nonlinear correction to the refractive index. This is a famous Kerr effect in optics. Light can actually spontaneously form such localized wave packets, which will be optical solitons. And after they were predicted, 7 years later, they were experimentally created in the famous work by 3 authors, Mollenauer, Stolen, and Gordon. So this is a famous picture borrowed from their experimental work. So what it shows actually the structure of localized solutions. So first, if they launch an input with a lower power, the nonlinearity is weak, and therefore it's essentially the linear signal. The linear signal will be gradually spreading. Then, if the power exceeds some particular value, the nonlinearity becomes important, and light, which is coupled into this nonlinear optical fiber, spontaneously creates one or several solitons. So this is a typical experimental trace which shows directly the observed form of the soliton. Its central part, at least, is quite accurately predicted by the analytical solution. And then these pictures, they show that if the power is taken still essentially larger, then instead of this fundamental soliton, it's possible, for example, here to create a bound state of 2 solitons, a second-order soliton. This is a breather, which I mentioned, which performs actually periodic internal evolution. Okay, then another more recent, but also extremely famous experimental demonstration of solitons was achieved in a completely different physical situation. Such solitons were created in ultra-cold atoms of ultra-cold gases of bosonic atoms, the famous Bose-Einstein condensates. So this gas of, typically the simplest case is the gas of lithium atoms. This gas is loaded into a quasi one-dimensional trap. Usually people talk about the Seeger-shaped trap. And then due to the attractive forces between atoms, this condensate can spontaneously split into several localized wave packets, which can be quite easily interpreted as solitons. So simultaneously, the experimental discovery of solitons in this atomic gas was reported in these two papers, one by the group of Hewlett from the Rice University in Houston, and the other by the group of Salomon in Paris. So this is a very famous picture taken from a snapshot, actually, of the local distribution of density in this gas. It is taken from the works of the group of Randy Hewlett. And so the interpretation of this picture is that this is a snapshot of the density distribution, which shows that the gas spontaneously organized itself into an array of 7 solitons. Okay. Then, these results are very well known theoretically and experimentally in effectively one-dimensional systems. And the challenging, simultaneously quite natural question is if one can extend this concept of self-trapping of wave fields and formation of solitons into effectively 2- and 3-dimensional situations. And here comes a challenge. So as we will discuss today, in many cases, there are quite accurate models of 2- and 3-dimensional systems, which admit, usually not in the analytical form, in the numerical form or in the approximate analytical form, that they admit solutions which can be easily interpreted as solitons. Usually, unlike the nonlinear Schrödinger equation in 1 dimension, the multidimensional equations are not exactly integrable. Nevertheless, they can easily create localized solutions. The existence of the one soliton solution is not a manifestation of integrability. In very many non-integrable equations, quite successfully can create single soliton solutions. So to formally obtain solitons, predict formally solitons in 2 or 3 dimensions is quite easy. What is very difficult is to make them stable. And here this is a crucial difference from 1 dimension. One difference is, of course, that fundamental equations in 1 dimension, which predict solitons, are integrable. In the multidimensional cases, with some few exceptions, they are not integrable. But this is more as a technical issue, because, okay, if we cannot solve the equation analytically, it's not a disaster. We can solve it numerically. However, a really fundamental problem is that in 1 dimension, solitons, for example, those nonlinear Schrödinger solitons, they are typically stable. But in 2 and 3 dimensions, they are not. So they exist as formal solutions, but they are unstable. And then a really important issue is to construct physically relevant models and then to perform the experiments, which would be able to provide stabilization of 2 and 3 dimensional solitons. So this fundamental effect, which makes 2 and 3 dimensional solitons unstable, first of all, in models still of the nonlinear Schrödinger type, this is called the collapse. Collapse means that actually due to the so first of all, to form any localized solution in any dimension, we need self-attraction of the wave field. Then in 1 dimension, as I already said, this self-attraction can be stably balanced by the linear effects, and then this gives rise to stable solitons. In 2 or 3 dimensions, formally speaking, the situation is similar. However, a drastic difference is that in 2 and 3 dimensions, this balance between the nonlinear self-attraction and linear effects such as dispersion and diffraction is not, the balance exists, but it's unstable. So if we slightly perturb this balance state, it will start to destroy itself. In particular, if we slightly compress this formally existing soliton, then in the multidimensional case, the self-attraction becomes actually a catastrophic effect, which starts to develop unlimited, unconstrained self-compression of such wave packets. And at least in terms of the mathematical model, after a finite evolution time, this solution will develop a true singularity. So this spontaneous catastrophic self-compression and formation of the singularities, this is called collapse. And actually, although formally speaking, solitons exist in such models, but they are unstable exactly because a small perturbation can actually push them in the direction of collapsing. And so, to illustrate these ideas, we can look we can take a simplest model. This is just a two-dimensional version of the nonlinear Schrodinger equation. Essentially, the same as we already discussed in one dimension, but simply with two coordinates, x and y, instead of the single coordinate. And then, if we want to look for solutions in the form of some stationary waves, we can easily substitute this ansatz. So mu is usually called, or this is, if you want, you can call it a frequency, or in application to Bose-Einstein condensates, it's called the chemical potential, or in optics, minus mu is called the propagation constant. And then, because it's a two-dimensional object, it may be quite natural to look for a solution in terms of the polar coordinates instead of the Cartesian coordinates, x and y. And then it's quite obvious that an ansatz which can be which we can try to use can include also this term in the phase. S is an arbitrary integer. Actually, this is what is frequently called the topological charge because it characterizes the internal topology of the state, or it's called also vorticity. And theta is simply the angular variable. Obviously, this and u is a real function of the radial coordinate. We assume that it will be localized to have a two-dimensional soliton. Then this u satisfies this ordinary real differential equation in the radial direction. Of course, one cannot solve it exactly analytically, but it's quite easy to solve it numerically, and it's quite easy to find the whole family of localized solution for any negative mu. Mu is the negative sign of mu is necessary simply to have the localized solution. One can easily have a family of solitons, so each negative value of mu gives rise to such soliton. First of all, if we take the fundamental soliton, fundamental, this means that the vorticity, which we can introduce, first of all, is not introduced. We just keep it equal to 0. Then we have only the function of the radial variable. It's obviously axially symmetric, isotropic. This is a distribution of the squared absolute value of this solution, and a numerically found solution, which can be very easily found. And for the first time, they were numerically found before the word soliton was coined. They were published in this famous paper, the theoretical prediction, in 1964. And the term soliton was coined by Kraskell and Zabusky in the next year in terms of the Korteweg-de Vries equation in 1965. Therefore, in this very first paper, they called it a self-trapped beam of light because they applied it to nonlinear optics. So because Townes, the third author of the paper, was a very famous optical physicist, usually these solitons are called Townes solitons. So this is the first soliton which was ever predicted in optics, even earlier than stable one-dimensional solitons were predicted, but it has never been observed experimentally. And the reason is that it is unstable. Okay, so some properties of such Townes solitons are, it's quite natural to characterize this localized solution by this quadratic norm integral of its local density squared of its local density, and then exactly the two-dimensional nonlinear Schrodinger equation with exactly cubic nonlinearity has a special feature, the conformal invariance, and it's very easy to demonstrate that although we have a whole family of solutions for any negative value of mu, but they all are degenerate in the sense that all solutions have exactly the same equal to of the norm. So this fixed value of the norm can be calculated only numerically, but nevertheless, it's very easy to prove that it's a single value. And then actually, we can take the version of the Townes soliton now with embedded vorticity when S is the integer, which is different from 0. And then each family for each value of S also has the same property of degeneracy. It has its own value of the norm, and this value, single value, is shared by all town solitons with embedded vorticity and with a fixed value of the vorticity. Of course, this single value depends on the vorticity. In particular, there is a simple analytical approximation, a rather accurate one, which can be derived, and it's valid for all values of s except for s equal to 0. And it actually demonstrates that naturally, with the increase of the vorticity, the soliton becomes, so to say, heavier or fatter, and therefore its norms grows approximately linearly. Okay, now this is an illustration of this collapse. So why this? First of all, the simplest town soliton, what is shown here is the evolution of its radial cross-section. So this is the input in the form of this numerically found town soliton. So for some time in the course of evolution, it seems that it remains stable, but then just without even adding any explicit perturbation, just due to the perturbation, which is small perturbations which are generated by error of the numerical truncation in the course of the simulation, the soliton starts to develop the instability. And what we see, the instability is exactly what I mentioned already. The solution tends to develop at the central point a very large amplitude, and eventually it will actually it will try to form a true mathematical singularity after finite evolution time. So this is what is called the collapse. Actually, in the case of the two-dimensional nonlinear Schrödinger equation with the cubic nonlinearity, it's called the critical collapse. And the reason to call it a critical collapse is that if we take an input, the collapse actually starts to develop if the norm of this input exceeds a finite critical value. And this critical value is nothing else but exactly the fixed norm of the town solitons. So if we have an input whose norm is exactly equal to it, or taken slightly larger, it will start the collapsing dynamics. If on the other hand, we take a norm which is slightly smaller, then this input will start to decay. And actually, this fact already suggests how, in principle, one can try to stabilize the two-dimensional solitons. Of course, it's necessary to add some additional terms to the equation, which should be, of course, the physically relevant terms, not just added artificially. But maybe, and we will see an example of that, maybe it's possible to find some terms which make it possible to create solid two-dimensional solitons whose norm which will exist with the norm smaller than this critical norm necessary for the onset of the collapse. If we will be able to create such a family of solitons with norm falling below the critical value, then they will be secured against the onset of the collapse. Simply, collapse cannot be initiated if the norm is smaller than the critical value. And then, as a matter of fact, such a soliton will have nothing to do but to be stable. We will see a direct example of that. Now, of course, we can also, for physical applications, it's also quite possible to consider the cubic nonlinear Schrödinger equation in 3 dimensions. And in 3 dimensions, again, we can formally find the soliton solution. It's completely unstable. And in that case, actually, the instability is, it also, it tries to develop singularity after a finite time evolution. But this instability is even more severe because in that case, formally speaking, the critical value of the norm is 0, which means if we take input with an arbitrarily small norm, it still is able to initiate the collapsing dynamics and eventually to blow up, to develop the singularity, the infinite value of the amplitude. For this reason, the collapse in 3 dimensions is called supercritical. And as we will see, there are nevertheless possibilities to stabilize 3-dimensional solitons in models of this type. But in that case, in the best case, what we can hope to do is to create metastable solitons. They cannot be made absolutely stable as ground states because the 3-dimensional collapse cannot be completely eliminated, unlike its 2-dimensional counterpart. Okay, now this was the instability of the of the town solitons in 2 dimensions with zero vorticity, fundamental solitons. As I mentioned already, it's possible to construct numerically their counterpart with embedded vorticity. This is a top view here or here. This is vorticity 1, this is vorticity 2. So naturally, the top view or distribution of the density will show the hole in the center. It's essentially the same as the fact that the commonly known Bessel function must vanish at the center. It's the same type of the mathematical fact. And then actually the investigation demonstrates that such vertical town solitons are vulnerable to a even stronger instability. Before the collapse will start to develop, they will demonstrate the instability against azimuthal perturbation. Azimuthal perturbations are perturbations which spontaneously try to break the axial symmetry of this soliton, of this vortex ring, and they try to, as you can see here, they try to split it into a pair of, as a matter of fact, into the pair of fundamental solitons. And then each fundamental soliton eventually will be destroyed by more slowly by the collapse instability. So in the case of the vorticity 1, this soliton is strongly unstable against spontaneous splitting into a pair of secondary fundamental solitons. In the case of vorticity 2, it's even stronger unstable against spontaneous splitting into a set of 4 fundamental solitons, and each will be later destroyed by the intrinsic collapse, also more slowly. Okay, so now once again, the fundamental problem is how to stabilize multidimensional solitons. So this activity was actually intensive relatively recently, both theoretically and experimentally, and there are some relatively recent reviews on this topic. So this is one rather relatively brief review, which for this reason I think is rather easy to read. Then there is another review which specifically published approximately at the same time, but it's specifically focused on the results for the stabilization of vortex solitons. As I mentioned already, it's more difficult than to stabilize fundamental solitons because vortex solitons are usually strongly unstable against specific splitting instability. And then actually there is a different topic related to this, but with different models and different solutions. These are multidimensional solitary-like objects in dissipative media, where in addition to the balance between self-compression and linear self-stretching effects driven by the dispersion and diffraction, there is we should simultaneously secure another balance between losses and gain. So there is, in many cases, multidimensional dissipative solitons may be also made stable, but this is today I will not mention them. Okay, and finally, there is a recently published book where actually very many results concerning the multidimensional solitons, both in conservative systems that I will continue to discuss today, and concerning the dissipative systems, they were collected in that book and actually can be found there. Okay, now remaining time will be devoted to this description, to the brief summary of how solitons can be stabilized in a physically relevant way in several types of important systems, and what kind of solitons, stabilized solitons, we will be able to see. Okay, so first of all, there is a rather relatively old activity, is a work which started quite some time ago, and this is based on the rather simple idea. If we again talk about, for example, 3-dimensional nonlinear Schrödinger equation, it's written in the form when the evolutional variable is called z, because in optics, physically the propagation distance, which formally plays the role of time, is not time, it's a propagation distance, it's called z. And tau is actually a temporal variable, but now it plays the role, formally speaking, of the third spatial coordinate. So up to this term, this is nothing else but the cubic, traditional cubic nonlinear Schrödinger equation. Now we can assume that there is a higher order nonlinear term, quintic term of with a higher nonlinearity with the opposite sign. So this term leads to self-focusing, self-attraction of the wave field, and this one actually competes with it because with the opposite sign, it actually gives rise to self-defocusing. And so there is then a very simple idea. If the system tries to develop the collapse will be arrested eventually, because when the amplitude will become quite large on its way to developing the singularity, then the quintic term, being the most nonlinear term, will become dominant, and because it's self-defocusing, it will simply arrest the further growth of the amplitude. Therefore, due to the balance between the cubic self-focusing and higher order quintic self-defocusing, there is a good hope to eventually to produce something localized and stable, so a multidimensional soliton. And then mathematically one can actually, in the 3 dimensions, one can look for these answers for the soliton. So here essentially we can again, this is written in the cylindrical coordinates. Tau is one of the cylindrical coordinates, and then r and theta are polar coordinates in the 2-dimensional plane, as we already discussed it. And then we can, generally speaking, look for solution also with embedded vorticity, with integer s. It may be 0, then we have the fundamental soliton, or we can have any integer value, positive or negative. Then we will have the vortex soliton, and this will be the radial equation. What one should solve numerically to predict solitons is this. Still, it's partial differential equation, stationary equation, because now we have 2 essentially coordinates, as radial coordinates and tau in the cylindrical system. Or in 2 dimensions, we can simply drop this derivative, drop the variable tau, and this will be the adequate description of the cubic quintic model in 2 dimensions. Okay, so for the first time in 2 dimensions, okay, first of all, it's necessary to say that as concerns fundamental solitons with 0 vorticity, the idea that the cubic quintic nonlinearity must stabilize them is obvious. And indeed, it was very easy to demonstrate numerically that the entire family of fundamental solitons is completely secured and becomes completely stable in this model. It's an almost trivial fact. Of course, it had to be demonstrated numerically, but it was obvious in advance. What is highly non-trivial is to try to see if a vortex soliton in the same 2-dimensional equation with the combination of cubic and cubic terms can be stabilized. Originally, people believed this is impossible, but nevertheless, for the first time, so to say, empirically, in direct simulations, this was demonstrated by the Spanish authors, Quiroga, Tejero, and Michinel. So this is an example of the numerical simulation. They first of all took, for example, a pair of 2-dimensional solitons with embedded vorticity, because this is a rather fat soliton, but nevertheless with a hole in the middle. The hole is created by the vorticity. So this is a vortex soliton. It's just the top view. Actually, they even took 2 of them and not only demonstrated numerically that each one is completely stable, but they also simulated collisions, interactions between them, and they demonstrated they simply bounce back and they are stable even against collisions. And then the question is, if such solitons in the models, in the media with cubic and quintic competing nonlinearities can be created experimentally, the answer is that the cubic quintic nonlinearity can be, actually, it really occurs in various optical media. It's a practically possible situation. And first of all, the simplest result, namely the demonstration of the stable, effectively 2-dimensional soliton with the 0 vorticity, fundamental one, was demonstrated experimentally in optics in this work by the group of people from Brazil and France. And then, actually, as concerns a more challenging possibility to create experimentally a stable soliton with embedded vorticity, thus far, no fully stable vortex soliton was demonstrated. However, there was a work in which actually it was demonstrated in the transient form. So this is an experimental picture. First, this is an attempt to create a vortex soliton, but with a very small power. Therefore, the nonlinearity is weak. and actually it becomes the evolution that we see is simply the linear expansion of the input. Now, if the input is made larger, then for some in the course of some finite propagation distance, we see actually this propagation of the stable vortex soliton. But later, because the medium has actually losses, dissipation, it starts to absorb the energy of the soliton, and because it loses its power, it eventually switches from the nonlinear propagation regime into the linear one, and then it becomes actually expanding quasi-linear object. Okay, then another challenging question is, okay, so in 2 dimensions, it was demonstrated numerically in some form experimentally that it's possible to, it's very easy to stabilize the fundamental zero vorticity solitons using the competing cubic and quintic nonlinearity, and it's not so easy, but nevertheless possible to stabilize solitons with vorticity. What about 3 dimensions? So in 3 dimensions, again, the stabilization of the fundamental soliton with no vorticity is, as a matter of fact, an obvious fact. What is very non-trivial is to try to stabilize the 3-dimensional soliton with embedded vorticity. And the result is actually already published 20 years ago, even more than 20 years ago. And the result is that only in the case when the vorticity is exactly 1, 3-dimensional soliton with embedded vorticity can be stabilized. So this is, roughly speaking, the view of such a solitons. Essentially, the distribution of the intensity seems like a torus or donut. In it, it has an internal hole. Once again, the internal hole is drilled by the embedded vorticity. And so what is illustrated here is its dynamical stability. One can take it applying rather strong random perturbations, and then in the course of the evolution, it quickly actually heals itself. It removes essentially the perturbations and quickly restores the expected unperturbed shape, which is stable. On the other hand, if one tries to create such a soliton with embedded vorticity 2, it seems to be always unstable, and this is a typical example of the simulated instability. One can take this input. Input is this vortex torus, so to say. It's the 3-dimensional solitons with embedded vorticity, which is 2, and then it always remains unstable against splitting. In this particular case, it prefers to split spontaneously into a set of 3 fragments. Each fragment can be understood as a fundamental soliton, and each of them is quite stable, but the stability of the fundamental soliton is quite obvious in this case. Okay, then a more recent result. This is stabilization of multidimensional solitons in the Bose-Einstein condensates. The cubic quintic nonlinearity, this is chiefly relevant to optics. Now we will discuss some other physically relevant model, which is appropriate in terms of the Bose-Einstein condensates. So this is what is called the spin-orbit coupling, and spin-orbit coupling actually is sort of a linear interaction between 2 components of the binary condensate, when we have the mixture of 2 different condensates. Usually, actually, it's essentially the same atom, but in 2 different hyperfine states. So there are many complex effects from condensed matter physics which can be emulated in a much cleaner form, much simpler form, in Bose-Einstein condensates in ultra-cold gases, and one of them is spin-orbit coupling. The spin-orbit coupling proper, it's a very important effect which was predicted and experimentally demonstrated in the physics of semiconductors. It means that when the electron is moving through the ionic lattice in the reference frame due to the Lorentz transform, the electrostatic field of the ionic lattice creates effectively the magnetic field, and this magnetic field couples to the intrinsic internal magnetic moment of the electron, and then it produces important dynamical effects. This is what is called the spin-orbit coupling. In Bose-Einstein condensate, of course, the physics is completely different. In particular, atoms are bosons, they are not electrons, but nevertheless, there is a possibility to map the spinor wave function of electrons in semiconductors into the two-component bosonic wave function of atoms in the ultra-cold gas. And then under special conditions, one can achieve a situation when the fundamental Hamiltonian, which accounts for the spin-orbit interaction in semiconductors, will be the same as the effective Hamiltonian in this two-component Bose-Einstein condensate. So this is how spin-orbit coupling was actually realized in ultra-cold gases. So there are some well-known works about this. And then the mathematical model for the Bose-Einstein condensate with the two components and with the spin-orbit coupling is written here. So in 2 dimensions, we can see this is a system of two coupled nonlinear Schrodinger equations. Usually in the application to Bose-Einstein condensates, they are called Gross-Pitayevsky equations, but this is the same as nonlinear Schrodinger. So these are two components, two wave functions of two different species in this binary condensate. So this is, we can immediately recognize the self-attraction as we've discussed before. And now the new terms are written here. So these are linear terms. They, as you see, they mix two components because in the equation for phi plus, we have contribution from phi minus and vice versa. So this is essentially the linear coupling between two subsystems. However, this linear coupling is actually expressed not in terms of wave functions themselves, but in terms of their first spatial derivatives. This is a specific feature of the spin-orbit coupling in the binary condensate. And now it was demonstrated thus far only theoretically that this system of two coupled Gross-Pitayevsky equations in 2 dimensions, quite unexpectedly, surprisingly, can give rise to completely stable 2-dimensional solitons. Naively, people thought that as well as in the 2-dimensional nonlinear Schrodinger equation, no matter what, we can easily have formal 2-dimensional solitons, but they will be unstable against the collapse. And now the unexpected result, in particular presented in these papers, was that solitons can become completely stable. So first of all, one can look for a solution in the form of the so-called semi-vortex. This means that what is compatible with the structure of the spin-orbit coupling is the possibility to look for a solution in which one component is simply a fundamental soliton with 0 vorticity, and simultaneously the second component carries vorticity 1. So this combination of vorticity 0 in one component and 1 in the second component, therefore it's called semi-vortex. It's compatible with a specific form of the spin-orbit coupling. And then this is a particular numerical solution which demonstrates the cross-section of, is quite easy to find the localized solution, a soliton. So the red line, this is the cross-section of the absolute value of the field which has 0 vorticity, therefore it has center, maximum of the center. Simultaneously, the dashed line is the cross-section of the absolute value of the vertical component, and therefore it vanishes at the center. And this is a stationary solution, and this is the stable solution. So this simple graph shows the most important results. It's a family of such spin-orbit coupled solitons, two-component solitons. And here the chemical potential is shown as a function of the total norm of this two-component soliton. Now, when mu, the chemical potential, is going to minus infinity, this family will tend to become equivalent to the very simple solution. It will be exactly the tau soliton in the 0 vorticity component, and the vortex component will become empty. So in that case, we will have just the unstable, we will have in that limit the unstable tau soliton. However, at any finite negative value of mu, we have the norm which is smaller than that limit value. It's obvious from in the plot, and there is no threshold necessary for the existence. Such a soliton, being very broad, may exist with an arbitrarily small value of the norm. And then this entire family is secured against the collapse because their norm is smaller than the critical value which is necessary for to initiate the collapse. Therefore, the collapse cannot commence. And this soliton, as a matter of fact, has nothing to do but to be stable. Indeed, it becomes completely stable. It plays the role of the ground state of the system, which otherwise simply does not exist. And by the way, there is a famous, not sufficient, but necessary stability condition for solitons, which are created by any kind of the self-attraction in a system with any dimension. Namely, if we have a family of solitons in the form the chemical potential versus n, the necessary stability condition is that the local slope, the derivative of this dependence, must be negative. This is, it's called Vakhitov-Kolokov criterion. It was theoretically discovered by in the former Soviet Union very long ago by two people with these names. Okay, then actually, very briefly speaking, it's possible to generalize the previous system. Now we can introduce additional nonlinear terms. We can assume that there are not only attractive interactions between atoms in the same component, but also attraction between atoms in two different components, because atoms collide and they can attract each other. In that case, if this new coefficient gamma is relative strength of the cross attraction in comparison with the self attraction, if it becomes larger than its critical value, which is 2, not 2, excuse me, 1, the following happens. When gamma is smaller than 1, we have stable semi-vortices, as we already discussed it. If gamma is larger than 1, semi-vortices become unstable, but there is a compensation. Then the system creates another type of stable solitons, which can be called mixed modes. Unlike semi-vortices, for them we cannot find an exact ansatz, but the approximate ansatz can be used as the initial condition, this one. And so how it's built, we have a zero component term in each, zero vorticity term in each component, and then also vertical terms with opposite vorticities +1 and -1 in the two components. And then it's quite easy to find numerically a stationary soliton. Its cross sections of two components is shown here with some splitting between their centers. And if gamma is larger than 1, they become stable and they are called mixed modes. So then it's necessary to explain why we have this switch of the stability between semi-vortices and mixed mode when this cross attraction coefficient passes a critical value 1. One can define the energy of the system and plot here for fixed value of the norm. One can plot the energy as a function of this coefficient gamma. So we see that when gamma is smaller than 1, the minimum energy of the energy is provided by the semi-vortices in the ground state, while the mixed mode exists too, but it's unstable because its energy is larger. But when gamma becomes larger than one, excuse me, then the minimum energy is provided by the mixed mode. It becomes the ground state, and on the other hand, the semi-vortex loses its stability. Okay, then there is another challenging question. It was a two-dimensional consideration. What about the fully three-dimensional version? Because the experiment can be performed with Bose-Einstein condensates in 3 dimensions, of course. And so this is actually essentially the same or very similar version of the model, also with this spin-orbit coupling represented by the first derivatives. Sigma is the vector of the Pauli matrices for the two components. This is called the Weyl type of the spin-orbit coupling. It's quite similar to what we already discussed. And here the situation is different because, as I mentioned, in the nonlinear Schrödinger equation with the cubic nonlinearity 3 dimensions gives rise to the supercritical collapse. And in the best case, we can only hope to create a metastable soliton, and this is possible indeed. So these are numerical results depending on parameters. So this is a distribution of the density in the two components. So this is the case when we have a metastable. It means it's stable against small perturbations, but maybe still unstable against very large perturbations because they can provoke the onset of the supercritical collapse. So this locally stable solution represents a semi-vortex, and on the other hand, for other parameters, what can be stable is not the semi-vortex, but the mixed mode. Then it has this fancy shape, but nevertheless, it's also a stable stationary solution. Okay, then I have a few minutes. Let me mention another quite interesting possibility is to stabilize 2- and 3-dimensional solitons in Bose-Einstein condensates. This is a possibility to add a competing nonlinearity, somewhat similar to what I mentioned already today. I mentioned the competition between cubic and quintic nonlinearity in optics. In BEC, there is another possibility. Because this Gross-Pitayevsky equation is derived in what is called the mean field approximation. Actually, it's sort of a semi-classical approximation. Then, back in 1957, there was a classical work was published by Li Huang and Yang. So Li and Yang, these are those famous people who received the Nobel Prize for the prediction of the parity non-conservation in weak interactions. And they analyzed the correction to the mean field theory produced by quantum fluctuations. So then this result was much later used by the Russian physicist Petrov, who works in France. And the result of Petrov was the following one. One can consider a binary condensate. One can consider these situations, and each component is self-repulsive. However, it's quite possible to have the situation when two different components attract each other. And then in each component, this Li Huang-Yang correction will give rise to the additional self-repulsive nonlinearity. And it will be, it will not be a quintic, it will be quartic, as if it's quartic. And it has a sign plus, it means self-repulsive. Simultaneously, it's possible to assume that the condensate, the two components, for the two components, the cross attraction is slightly stronger than self-repulsion. And therefore, one can assume that two wave functions of the two components are simply equal to each other, and one will end up with a single Gross-Pitayevsky equation in which the cubic term is self-attractive, it tries to construct unstable solitons, and then the Li Huang-Yang correction is quartic, self-repulsive. For the strong nonlinearity, it becomes dominant, and it may help to stabilize the solitons. Okay, and then this is first of all the result of the numerical simulations. It shows the radial structure of such soliton-like objects. Usually they are called not solitons, they are called quantum droplets. They are called quantum droplets for the following reason. Because of the competition between cubic self-attraction and quartic self-repulsion, if you want to create such a soliton with a very large value of the norm, its amplitude will be limited. It cannot become larger than some maximum value. But then, in order to accommodate a large norm, this soliton will become very broad. And therefore, effectively, because the density cannot be made larger than some limit value, it seems like a quantum liquid. For this reason, such a self-trapped localized object, which is filled by the quantum liquid, it's called the quantum droplet. But essentially, this is like a soliton. Okay, so then a very interesting fact is that such a fundamental quantum droplet, fundamental, I mean, without vorticity, will be stable is quite obvious. What was not so obvious, a possibility to create it experimentally, and quite surprisingly, just a couple of years after the prediction by Petrov, two groups simultaneously reported the actual creation of such a stable quantum droplet. The first experiment was published by the group from Barcelona. Actually, the geometry in the experiment was quasi-two-dimensional, because in the third direction, it was strongly trapped by the external field. But nevertheless, so here, this is the experimental situation when the number of atoms is too small, then everything spreads out. Here is a situation when the number of atoms is too large, and then the input is destroyed by the spontaneous collapse, by the blow up. But with the correct number of atoms, it forms a stable soliton-like object. This is a distribution of the density, and this is exactly the quantum droplet as predicted by Petrov. And this is another experiment. The difference, this experiment was performed by the group in Florence in Italy, and the difference is that this is a fully three-dimensional quantum droplet, because here the effect of the external field was negligible for the shape of these objects. And then one more thing, one more theoretical result. once such fundamental quantum droplets are, it's quite obvious theoretically they're completely stable. A more challenging issue if one can create such objects with the embedded vorticity. Indeed, theoretically, it was demonstrated. First of all, it can be demonstrated in 2 dimensions. So these are typical examples. This is top views of the density distributions in such vortex droplets with vorticity 1, 2, 3, 4. These 3 objects are stable. The 4th one is not. So these are cross sections, and this is the summary of results. Such vertical droplets, they exist as stationary states if with the growth of the internal vorticity. The norm exceeds this particular minimum value, but they are stable if the norm exceeds a still higher value here. Okay, and then this was the result for the vortex droplets in 2 dimensions. The most challenging issue, of course, is to try to predict stable 3-dimensional quantum droplets with vorticity. Indeed, this was done as well in this, numerically in this work. And so this is an illustration. First of all, in many cases, of course, such 3-dimensional droplets with embedded vorticity, it's similar to what we already saw in another example today. This is like a vortex torus, a torus whose shape is supported by the embedded vorticity. It can be in many cases unstable. If it is unstable, it splits spontaneously into fundamental droplets, which are stable then, but in a properly chosen parameter region, one can numerically find and clearly demonstrate the presence of the stable solutions for the 3-dimensional droplets with embedded vorticity. So this is the simplest example, a stable droplet with vorticity 1, and also it's even possible to find examples of stable droplets with embedded vorticity 2. So there is some review paper, relatively recent one, on this topic, and then we arrive at the conclusion, because actually I'm running out of time. So the conclusion is that there is a challenging problem how to extend the concept of solitons from the commonly known 1-dimensional geometry to the 2- and 3-dimensional geometry. Then there is a fundamental problem that, formally speaking, in relevant models such as the multidimensional nonlinear Schrödinger equation, it's quite easy to construct formal stationary solutions for solitons, both fundamental ones and with vorticity. But a severe problem is their stability, because in the simple case, the fundamental soliton tends to be unstable against the collapse, and the vortex soliton tends to be unstable against spontaneous splitting. And then it was, more recently, it was found that there are various possibilities, physically relevant ones, to consider the models in which additional terms make it possible to stabilize multidimensional solitons. In particular, quite interesting are recently elaborated possibilities. One was still elaborated only theoretically. This is the stabilization of 2- and 3-dimensional solitons by the spin-orbit coupling. And another one, which is really impressive because it was realized experimentally, also without vorticity, of course. This is a possibility to create stable quantum droplets by means of the quantum correction to the mean field theory for the Bose-Einstein condensates. Okay, and then of course the remaining problem is to produce more experiments in this field and to demonstrate examples of stable solitons experimentally in many cases when they were predicted theoretically, but still no experimental results are available. As I said, theory can also be developed. In particular, it's possible to consider situations when in 3 dimensions one can try to construct topologically organized solitons, not simply as vortices, but for example with 2 values of the topological charge. This may be the so-called skyrmions, which are very famous objects in nuclear physics, as well as the physics of semiconductors, but theoretically they were already predicted, for example, in 2-component Bose-Einstein condensates. But of course, this is still a purely theoretical analysis, which is quite far from the experimental realization. So I believe in any case, I should stop here. So thank you very much for your interest.
Dear Professor Melamed, thank you very much for the very interesting talk.